Welcome back, everybody. The topic this week is to try to wrap up this topic about Boltzmann machines, which were the first type of energy-based models which were introduced back in the previous millennium. So when you say millennium, it sounds like ages ago, right? If you say previous century, then it sounds a little bit better. But the Boltzmann machines were extremely popular, but they are difficult to train. So in a certain sense, the kind of lectures which we started with last week and the way it will evolve today as well focuses more on Boltzmann machines, because from a pedagogical point of view, it's easier to understand what happens, and it's easier actually to see how we can implement it. But Boltzmann machines have actually been replaced by general energy-based models, where the models, if somebody could just lock the door there, right, or close the door, right? Because that voice in the background was a little bit, okay. So the Boltzmann machines, in a certain sense, serve them as a kind of pedagogical model for us. However, in the last years, and this was actually right before COVID, this kind of energy functions have been replaced by a standard neural network or convolutional neural network. So you sample from a probability which has as a function say a convolutional neural network. And these models have been extremely powerful. And they are some of the models which fuel software, which probably you may have heard about, DALL-E 2, or image generation or image gen. These are very popular softwares which are on the market. And so this is in a way a field which evolves swiftly. So you would say that pre-COVID, general adversarial networks and variational autoencoders were extremely popular. But nowadays, these type of models and also diffusion type of models are the models which in a way dominate the market when it comes to generative models. Also, when it comes to generative models, this kind of diffusion-based approaches, which some of you may be familiar with, uses not metropolis sampling or Gibbs sampling in a Markov chain, but it uses something which is called Langevin sampling. And for those of you who have a background in, let's say, mechanics or fluid mechanics, you probably heard about the Langevin effect. So Langevin sampling is actually a very efficient way of sampling. But in order to understand what these models actually mean, it is extremely useful to look at Boltzmann machines, because that contains the basic pedagogical elements in constructing these more advanced diffusion models. So for the rest of the semester, after we've done with that, we will look at diffusion models, but we will also, and we have to, say something about variational autoencoders, which have been extremely popular, and the same with the general adversarial neural networks. And that essentially completes the rest of the semester. So the second variant of the project deals with implementations of these models. So it could be a Boltzmann machine if you want to implement that on, let's say, specific data sets. It could be classification of images like the MNIST set of data. It could be other type of data sets. Some of you would perhaps like to implement a Boltzmann machine for more physics-like problems. So these are the type of problems which you could actually study in the second variant of the project. However, many of you are working on just one big project, and then it makes sense to continue with that specific project. So if somebody's working with, let's say, physics-informed machine learning, this is something which may actually take more time than just one of the projects. And so if you are into that, I mean, keep doing that. However, I think it's important to actually have an understanding of what generative models mean and why they are so popular. So if you look at the list of topics which we have, you will see that there is a link to programs which you have in the textbook by Babok and Ball. So they discuss how to implement a standard Boltzmann machine. And then if you go into the textbook by Foster, there's a link to the GitHub address of that textbook. So you have access to both textbooks. And essentially the Jupyter notebooks are extracts of every chapter. And there is a discussion actually on this energy-based models, which then use the Langevin sampling. So we will start looking at the Langevin sampling towards the end of the lecture. So the beginning here is going to contain some elements of repetition from last time, because I want to bring back some of the basic equations which we encountered last time. So I want to repeat a little bit about Boltzmann machines, and then also remind you a little bit about Markov chain Monte Carlo, which is the essential recipe for being able to make the simulations. Then when you use a Markov chain algorithm, you need to have a sampling rule. Now, last week we discussed the standard metropolis algorithm, which is one of the standard sampling rules for accepting a new sample. Now, the metropolis algorithm relies on you being able to calculate the whole probability distribution. That is extremely time consuming because your probability distribution is going to have many, many variables. So in general, the probability distribution can be an infinite dimensional quantity. So the metropolis algorithm becomes a little bit, how to say, more computational involved, and it's normally not used in this kind of Markov chain Monte Carlo simulations. The algorithm which ruled the ground till roughly 2015, 16, 17, if you go into the textbook by Goodfellow et al., and the sections which you see here are the essential ones. This textbook was written in 2016, and you could say that many of the things which are there when it comes to generative models have actually been bypassed. So this tells you a little bit how fast the field is moving. And but the basic principles are there, and these are the basic principles which we will try to dig a little bit deeper into today. So the type of sampling which replaced the metropolis sampling is what is called Gibbs sampling. So Gibbs sampling is based on what is called the conditional probability, which we defined last week, and which we are going to remind you of today. So the conditional probability is then a probability which acts on just on one of the variables which you have. And that means that all the other ones are unchanged, and that makes it easier to sample. However, the Gibbs sampling has what we call long correlation times. So you need a lot of cycles in order to reach what is called the most likely state. So the Gibbs sampling is also seen as something which is computationally expensive when it comes to training large models. So just keep this in mind, because one of the bottlenecks for Boltzmann machine implementations has simply been the computational expense. So you're always searching for something which is faster. And this is where Langevin sampling has taken over. And who knows what is the next sampling. But this field is actually moving quickly, and the way you sample these probability distribution is very, very important. So let me remind you of some of the essential elements of this kind of generative models. And you will see some of them in the lecture notes here. So I'm going to go a little bit slowly through this. And what we typically have is a probability distribution. And we have normally assumed that this probability distribution is given by stochastic variables, which are defined by this axis, which you see here. And you have a domain of events. And this probability distribution, which you see here, is often assumed to be independent, and it describes identically distributed stochastic events. So this could be a product of Gaussians, just to give you an example. And what we also assume when it comes to these Boltzmann machines is that we have a set of additional parameters. And these additional parameters give us more flexibility in the training. And these parameters are then so-called hidden variables. And we have a new set of stochastic variables. So that means that we have a probability distribution, which is given in terms of an event x of I and an h of j, and then we have the parameters theta. So theta are the parameters we want to optimize. And then this is given by some function. And this is where you would typically have you could have a Boltzmann distribution. You could have something which looks like a Boltzmann distribution. So that means that this quantity which you see f here is often an exponential. There is also an important mathematical assumption about f. So since these are probabilities, f is a quantity which is larger or equal to 0. In many probability distributions, you essentially don't have it equal to 0. If you think of an exponential, you actually have to take the limit going to infinity when e to the minus something. So in principle, it gives you even a negligible probability in most actual calculations. So the function f, which you have there, is normally a positive function. That's a very important aspect. And it fulfills all the properties of a probability. So what you have there, when you sum up over all the h's and x's, this probability should be normalized to 1. So the z is normally called a normalization factor. But since the standard form for this f is an exponential with some arguments, then it's very tempting to just call this a Boltzmann distribution. And then you have a link to statistical physics. It's very much used in statistics as well in mathematics, but then this leads to the standard Boltzmann distribution. Now, this function, as you see here, is actually now given by a sum over all these x's. So later, when we are going to look at a model, a specific model for this function f, then we need to change the notation a little bit here. So as it stands now, it's pretty general, but then we have to tailor it to a Boltzmann distribution or an energy-based model. So the reason why this is called an energy-based model, so let me just quickly switch over to the whiteboard here. So let me quickly remind you of that. So what we have defined is a probability distribution where we have a p of x of I, of h of j, and then we have some parameters theta. And this is given by some function f of x of h of j, and then we have these parameters which we want to optimize divided by z of theta. Now, this function which we have here, this f, is in its most common disguise written as an exponential, and then we have minus, and then we have e of some x of I of h of j of theta. This is the most common model which we use. Now, in our case, in the applications of the standard Boltzmann machines, what we are going to do then is to replace this e. So the example for a Boltzmann machine so this is just a reminder of what we did last time. Then this function e of x of I of h of j of theta can be written as, and now we have to be a little bit careful here with the notation which we are going to use. So I'm going to change a little bit the notation here, and you will see why I need to change the notation. So in general, you can keep x of I and h of j because this is a probability of finding these instances. But this function is something which I'm now going to rewrite in terms of a vector x and a vector h. And one of the standard functions, which you will see, is something which looks like this. And then I have an x of I, and you will see why I had to change the notation here. And I'm going to bring in a slightly different way of looking at these x's and h's. So I have a b of j of h of j, and I'm not specifying the sums here. And then I have a sum of I and j, and then there is an x of I, a wij, and an h of j. So let me try to repeat and explain again what we discussed last week when it comes to the Boltzmann machines. So in order to see that, we need to make a drawing. So what you see here is normally called a binary Boltzmann machine. This is the most common case. And then we are assuming that these x of i's take values 0 and 1. And the h of j's take values 0 and 1. What we would have then would be a set of nodes. And we would have a set of visible nodes. So this is the visible one. So this will be my x1, or let's call it x0, x1, up to some x of m minus 1. So I'm just labeling them a little bit differently from last time. And then I have an h0, h1, and this goes up to h of n minus 1. So I have n hidden nodes. So these become parameters of the architecture. And then I have m visible nodes. So if I'm training a figure, an image, with like the MNIST data set, where I have 28 times 28 pixels, then I would need, if 28 times 28, that should be 728, if I don't remember exactly, something like 700, then I would need 700 visible nodes or input nodes. So when you look at this model, which I have here, then what I have are so-called biases. So I would have an A1, etc. And then I have a B0, B1. So these are the biases, these two terms here. And then I'm connecting the different nodes with each other. So we are looking at a fully connected system. So like this one would be a node W11. So we have the biases A of I and B of J, and weights, which we call theta. No, sorry, not theta, but W. Oops. So that means that I have a set of parameters. So if I do this, what I get then is a set of unknown parameters, which I'm going to train. So the unknown parameters, they are collected in this container theta. So they're given by theta, and then I have a vector A. I have a vector B, so hopefully I can distinguish this one from the quantities with subscripts. They look like as they are bold-faced. So these are vectors and matrices. The uppercase letter is a matrix. So these are the parameters which we need to train. Now, if you then go back to the kind of definition which I had, this definition here, I need to change this definition a little bit. So what I need to define now, if you look at my possible values, which you have here, each set of values defines a configuration. So I can now have, suppose now that I have m equal 2. So that means that I have x0 and x1. And then I have n equal 2. So that means that I have 2 hidden variables, like that. I can now define a configuration. So what I would have then is a configuration which I'm going to call X, and that is a vector. And that contains a specific set of values. So I could have the following. I could have 0, 0, right? So these are now stochastic variables which take values 0 and 1, or -1 or +1. I can have 0, 1. I can have 1, 0. And finally, pretty obvious, I can have 1, 1, right? So these are my configurations for X. And then you have similar configurations for H. So that means that what I would have then, in this specific case, I have 2, since I have a binary system, to the power of n configs for X. And I guess you don't get offended if I don't write it, but I just state it. You have a similar one for H. So you have 2 to the power of n configurations for H. So that means that in this specific case, when I'm now looking at the partition function, I need to change my notation a little bit. So if you go back to this energy model, which we put up, so this energy model is something which I now can write as an E of X, of H, and these parameters theta, and I can write it out as, and I had a minus sign here, and then I have a minus in the exponential, and I can write it out as A transposed times X minus B transposed times H, and minus X transposed times W times H. Because now, the only thing I'm doing is I'm actually rewriting these sums, which previously were simply I equals 0 up to 1, or n minus 1. And this was given by AI, xi, and then I had minus j equals 0 up to n minus 1. And then I have bj of h of j, and minus, and then I have aj, m minus 1, and n minus 1 of xi, wij multiplied with hj. So this is just a more compact notation. And now you see that the original notation which I introduced, where I had subscripts on xi and hj, this is something I need to change now for this specific model. So that means that my partition function now is given by, so this z of theta is now a sum over all the possible configurations. And in this specific case, with a binary model, this now has, sorry, not that one, but it starts with the first configuration, which I label as 0, up to 2m minus 1. And then I have to sum over h equals 0 up to 2n minus 1. These are the possible configurations. And then I have this function, which is given by f of x, and then h, and theta. Okay? And if I look at a Boltzmann machine, this is nothing but a sum, or if I take this model which we set up now, 2m minus 1. For this specific case, we have 2n minus 1, and then I have e to the power of a t times x, because I'm having e to the minus e, and I have minus in front of these, so that becomes just positive, plus b of t times h, plus, and later we are going to see how we can rewrite this. So this is my normalization constant. Now, one thing you see immediately, like the petit case I looked at now, where m is equal to 2 and n is equal to 2, only 2 possible values. So that means that if you look back at the network here, what you have then is just 2 nodes, 2 in the visible layer and 2 in the hidden layer. If I do that one, this is something which we can easily sum up. But in general, if I now take mnist with 32 times 32, bits, then I would have 1,024 input nodes. So that means that you would have 2 to the power of 1,024. You don't want to do that sum. So we need to have approximations to it, okay? So you see the bottlenecks here. So the partition function is the kind of ugly object which we don't want to deal with. And this is where we have these different techniques which we are going to remind you of what we did last time. So we're just going to set up the way we are going to run the simulations, where we are going to optimize the log of the probabilities. So if we now look at the probabilities, what I will have is a probability P of X of H. So now this is just one given configuration. Keep that in mind, just one specific configuration, just one of them. And this is now given by this function, which for this binary case, so I'm going to put a BB, binary, which is this simple example. This is going now to be given by A of T of X plus B of T of H plus X times W times H. And this is divided by Z of theta. In general, what we have, the general probability distribution is H of theta. And I'm trying to make this boldface to let them indicate that these are configurations. This is simply going to be given by X of H and then theta divided by Z of theta. And what we did last time was actually to set up the optimization problem as a maximization of the likelihoods. So that means that my total probability for the total domain X, the total number of X's, so this is an uppercase X and an uppercase theta, H, is simply going to be given by the product of all the individual ones. But let's wait a little bit and let me try to rewrite some other quantities. So what we also defined last time was what we call the marginal probability. And that for X, this is simply now the sum over all the values H. And for a binary case, this is 2 to the power of n, all the possible H values or configurations which I have. And this is now given by P of X of H, sorry, not that one. And I have a similar one for H, which is then the sum over all the X's, all the possible configurations. So that is called the marginal probability. But then, since we are going to do GIP sampling, we need something which is called the conditional probability. And the conditional probability is then defined as follows. So if we now have P of H given X, this is actually given by the probability, and now I'm skipping theta. So I'm just leaving that out just for notational simplification. So we are coming back to the details. So I'm skipping theta here. This is now given by the probability of X and H divided by the probability of being in X. And similarly, I have the probability of X given H, and this is given by the same quantity divided by P of H. So this is something which also leads to Bayes' theorem. So many of the things which we are discussing now are tightly linked with Bayesian statistics. Some of you may be familiar with that. And Bayesian statistics uses also Monte Carlo, Markov chain Monte Carlo, together with Gibbs sampling in order to sample from the probability distribution and obtain this conditional probability, or what's normally called the posterior probability. So you would have typically a model, because you can write, if you then think of Bayes' theorem, this quantity here can be written out, and now you would have a model for H given X, multiplied with the probability of X, divided by this P of H here, the marginal probabilities. So this is Bayes' theorem from the probability of X given H. And you can interchange this and get the posterior probability for obtaining H given X. This is essentially what you see here. This is Bayes' theorem. So generative models have lots of commonalities with Bayesian statistics, especially when it comes to the mathematical way you sample the probability distribution, which is essentially Markov chain Monte Carlo with some specific sampling rule. So when it then comes to what we did last time, I'm going to bring back some of the slides. So I'm not going to repeat everything, but I wanted to bring this up here so you see a little bit more clearly where we are going. So one of the things which we did last time was also to set up the quantities which we want to optimize. Now, let me revert back a little bit to this notation here, because that's, now you could think of these X of i's of just being one specific configurations without us having specified a given model. So I hope you can forgive me if I just switch back from a specific case, which is the explicit equation for the Boltzmann machine, to a general case where these Xi's and Hj's haven't been defined yet, okay? So Xi could be a given configurations of the X's. So one of the things we did then was simply to start optimizing this quantity here. So we are now looking at a specific set of outcomes for the domain X, and this is given by the product of all these probabilities, which again, since this is the marginal probability, so at the end, when we look at this Boltzmann machine, what we want is not the probability of the hidden layers, because they are hidden and they are not interesting. It's the same as when you do a neural network, you have the input and the output, and you're not interested in what's between, because that's something you use as additional degrees of freedom to optimize a complex function. So at the end, what you want is P of X. And this P of X, the way you assume everything is distributed is according to a product of probabilities for the individual events. So this would be an individual configuration, or it could just be the individual value X of I. So now we don't specify the specific function which you see here, this function F here, okay? I hope you can forgive me jumping from the specific case where we have a model for the function and where we need to pay a little bit attention what X means to the more general case which you see here. Now, this function is now simply given by these products of the individual probabilities. And then we have the partition function here. And this is the quantity we want to optimize. So at the end, we want to find an optimal set of thetas which maximize the probability. And as we said last time, it's meaningless to minimize a probability. Nobody's interested in a marginal probability. We want to have a maximal probability. So I hope everybody sees that that's the reasonable thing to do here. And the typical thing you end up doing then is to simply do a maximization, and then you find the optimal values of theta. And the equivalent case is to optimize the logarithm. And this means that you need this quantity here. That's what you need to calculate. And as you saw from even the simple case with a binary Boltzmann machine, this Z here becomes an ugly animal to evaluate. I shouldn't say ugly animals. All animals are sweet. Ugly beasts, perhaps. So the thing you end up with is actually this equation here. Now, this equation here is actually in the literature. There's a lot of, how to say, interesting observations about this equation. And I'm coming back to that. So if you have looked into the textbook by Goodfellow et al., I'm going to bring it up actually, because some of these things are a little bit amusing to look at. But this term here is called the positive phase. And this term, which you see here, is normally called the negative phase. This is something, because we have a model here. So this is something we know how to sample from, because you have a model, even if it's a complicated function. And then you have the partition function, which is the animal or the beast which is difficult to evaluate. And this is something which we last time rewrote. So when you look at the partition function, the derivative of that one, you can rewrite it like this, which again means that you have it, you have this equation here, which you then, since this is always a positive function or larger or equal than 0, you can rewrite it as the exponential of log of f. You can rewrite it like this. And then finally, you end up with this expression here, which is nothing, as we discussed last time. So I'm going a little bit quickly through this because we went through that last time. This is actually given by the expectation value of this quantity here. So that means that you need a Monte Carlo sampling to actually estimate that specific function. And this is where the Markov chain Monte Carlo comes in, because you're calculating an expectation value. And this is what makes it feasible to calculate the derivative of the partition function. So what we have done now through these manipulations from this equation here, taking the derivative, and then the expectation, since this is just transforms into the expectation value, the log of the function f, where we now have summed away the hidden layers. So you see, there's a lot of mathematics which needs to be done. The nice thing with a Boltzmann machine is that you have an analytical expression for these, which you can plug into your codes. And these analytical expressions is something which we will derive after the break. And they're actually not that difficult to set up. If you have a binary Boltzmann machine, or if you have a Gaussian binary or a Gaussian. If you go beyond that, then these derivatives need to be calculated numerically. And that becomes time consuming. So there are bottlenecks here. And this is one of the reasons why, even if they were extremely popular to roughly 210, before, let's say, CNNs took over and many of the standard deep learning methods, the basic machinery which you see here, these equations which we have to implement, if you look at this equation up here, this one, this is the one we end up implementing when we do the Monte Carlo Markov chain sampling. We can actually replace this function f with another type of energy function. And what people have done is to replace this function f with a convolution neural network. So you have e, the exponential, to the power of a convolution neural network. So you can actually, and this was the kind of breakthrough from 2016, 17, where people just considered, why don't we replace, instead of having a standard energy function, as the one you saw in the notes, we just change that to something more complicated, a neural network. And that means that you will sample these x's with an exponential of a convolution neural network. And this has proved extremely powerful and has led to generative models which are widely used in nowadays. Like this DAL-E, which some of you probably have downloaded. I actually had it on my cell phone to generate images. I was not too happy with them anyway, because when I put quantum into it, or quantum machine learning, or things I'm interested in, it just came out in a very strange way. But if I wanted to have houses or other things, then you could get pretty nice things. You probably played around with these kind of image generators, right? So the whole thing now is that we have the term with a positive sign and a term with a negative sign. So what I want to do now is just to bring up, instead of me writing it down, I just wanted to bring up some kind of neat interpretations which you will find in the literature. And this interpretation is actually taken from the textbook by Goodfellow et al., which you can access. You can download it. You can just go to the website. And I just wanted to highlight, so you will see basically the same equations which we have here. So they are going through, this is in chapter 18. And then there are some interesting statements here. So if you, so you can view this Monte Carlo Markov chain as approaching a maximum likelihood as trying to achieve a balance between two forces. So it's a little bit extending it, but it follows this kind of physics way of thinking. And one pushing up on the model distributions where data occurs, and another pushing down on the model distribution where the model samples occur. So this is the negative part of that equation. So that means that if you go back here and you look at the equations which we are calculating, so when we take the derivative, so we have one with a positive phase and one with a negative one. And this is where we calculate an expectation values and we have samples. And then you can continue this interpretation here. And let me just bring it up. So there's an image here where you can look at the positive value or the positive phase. So the positive phase, you sample points from the data distribution and push up on their unnormalized probability. So that means that the points are likely in the data. This point means that points that are likely in the data get pushed up or more. And here you have something where we push down, we sample points from the model distribution and push down on their unnormalized probability. And this counteracts the positive phase tendencies to just add a large constant to the unnormalized probability everywhere. Now you will then see statements like these. So the two forces correspond to maximizing the log of the probability distribution and minimizing the log of the partition function. Because the negative phase involves drawing samples from the model's distribution, you can give some interpretations to it. And one of the interpretations is that finding points that the model believes in strongly, and because the negative phase acts to reduce the probability of those points, they are generally considered to represent the model's incorrect beliefs about the world. So this is a little bit how to make it a little bit more far-fetched. But then it's even more far-fetched here, and they are frequently referred in the literatures as hallucinations or fantasy particles. In fact, the negative phase has been proposed as a possible explanation for dreaming in humans and other animals, in the sense that the idea being that the brain maintains a probabilistic model of the world and follows the gradient of log p when experiencing real events, while awake, and follows the negative gradient of log p to minimize log c while sleeping and experiencing events sampled from the current model. So these are, how to say, interesting observations, but you can make this kind of ways of interpreting the way you actually optimize these two quantities. But essentially, that equation which we saw, whether you deal with a standard Boltzmann machine or another type of function, is essentially what stands in these calculations of energy-based models and generations of the optimal probabilities. So to summarize, you would typically start with a product of the individual events. You want to optimize this quantity, and in optimizing that quantity, you have to optimize and calculate the derivatives with respect to the parameters. And this gives us now a set of equations which have to be computed by using a Markov chain Monte Carlo. So I will not repeat the basics of Markov chain processes. Last week, we also discussed the Metropolis algorithm, but now we are going to, after the break, we're going to look at the way we perform this sampling, and the way we're going to perform it is by Gibbs sampling. And this is now something which has been superseded by Langevin dynamics and Langevin sampling. So look at this kind of lectures, a more kind of historical progress towards diffusion models, which we will discuss partly next week, but also towards the end of the semester. So before we dive fully into diffusion models, we also have to say something about GANs and variational autoencoders, which are popular techniques in order to generate probability distributions. So this was a kind of meant as a kind of repetition of what we did last week, but also as an input to what is coming next. So what we are going next is actually to look at how we set up the Gibbs sampling and how and what it means, and how we can actually find the analytical expressions for the marginal probabilities and the conditional probabilities in the setup of a Boltzmann machine. And then at the end, we are going to say bye-bye to this, because these are techniques which are less practical nowadays, but they have a, what I would say, a pedagogical input to the usage of energy-based models and diffusion models, which nowadays are extremely popular. Any questions so far? So I hope you see the overarching themes before we go into the gritty-nitty details of Boltzmann machines. So if we look at this energy model, which we had before the break, when we dive into the Boltzmann machine itself, then we can have a simple model, which is a binary one. And we are going to look in particular, to be more specific today, we are going to actually look at the explicit derivation of the marginal probabilities and the conditional probabilities, which you need in order to write your own code for a Boltzmann machine with a binary case. Now, you can make this more complicated if you want to. So if you look at this specific case, and we are going back to that when we look at the drawings of a network, in this specific case, we don't have internal connections in the visible layer, and we don't have internal connections between the nodes in the hidden layer. That is often something which is called a deep belief network. You can actually stack these Boltzmann machines. Before we break, we just looked at one with one hidden layer only. You can stack more hidden layers, and you can also put connections between the nodes in each layer. That gives you more points to train, and it becomes more difficult to train. So this restricted Boltzmann machine, which we looked at before the break, is the one which has been the kind of standard Boltzmann machine, which people refer to when they think of Boltzmann machines. So as you saw, this is now the energy function, which we looked at before the break, and that gives us a compact probability distribution here. And after the break, we are going to sum over H and sum over X to get the marginal probabilities. And it shouldn't be a surprise that you will get a pretty simple function, which I've seen many times before. So the probability for H, for instance, is going to be proportional with a sigmoid. And especially for the binary case, when you replace the visible variables with continuous variables, then you could typically use a Gaussian distribution for those. And that gives you a Gaussian binary Boltzmann machine. And you can make this more complicated, but then the analytical expressions for the quantities are going to be more involved, or you have to evaluate them numerically. So there is always a balance you have to strike between having nice, simple analytical expressions, because if you look at some of the results, and one of the things you will need in the calculation of the gradients are the derivatives of this function with respect to the unknown parameters. So when we are taking the derivative with respect to theta, it means actually that we need the derivatives with respect to the weights and the biases. And for the binary case, this is extremely easy. you have simple, nice analytical expressions. There is no need to spend time on evaluating complicated expressions for the derivatives. So normally a Boltzmann machine is popular because it has simple analytical expressions for the different probabilities. So we are going to go through some of these derivations, and it's not that exciting, but I wanted to see how you go through them. And what I want to do before that is now to say a little bit about the way we perform the sampling. So last week we discussed, or we revisited Markov chain Monte Carlo, what that actually means. So we have a Markov chain, and after some movements back and forth, we reach what is called the most likely situation, or the steady state. And that means that we often waste a number of cycles before we reach that stage. So if you look at the algorithm, what I'm going to do is to simply take from the textbook by Goodfellow and Benjo and Coville. And this is in section 18.1 and 18.2. And this is one of the ways you would do that. So if you now look at the algorithm, you need to set a learning rate. So this is what they call the step size. This is the learning rate. You can replace that with more advanced algorithms. You can have ADAM, you can have root mean square propagation, you can use ADAGRAD to update the learning rate, or you simply just fix it to a constant. So everything you've been doing in machine learning when it comes to the learning rate is something you could apply here as well. This is the simplest possible way. Then you need to set up the number of steps which you do. Now, what you do then is then to train on a set of data. So you have a why not converge, you sample a mini batch, so you set up small batches of data, and then you find a set of samples, and then from the training set, you calculate the gradient. So this is a quantity you actually want to calculate. It's the derivative of this function here. This is the one we need in the calculation of the expectation value, which we defined before the break. So that means if we go up a little bit, it's this quantity here, which is being set up. The other quantity, this one, is a little bit easier to set up, but you have to set it up because we have a model for F. So the expectation value is the one which is important in the setup here. And then you would initialize a set of new samples. So a Gibbs sampling, what it is doing is actually it runs through the set of samples several times. So if you think of a standard Metropolis algorithm, you run through all the samples, and every time you calculate the ratio of probabilities. For Metropolis sampling, you need to set up the whole probability. In the Gibbs sampling, what you do then is that you calculate the conditional probability for one of these x's, and you leave all the other ones the same. Leaving all the other ones the same means that your computational expenditure applies only to one of these parameters every time you perform a sampling. That is a difference between Gibbs sampling and Metropolis sampling. But you need them to have an analytical expression for the conditional probability. So you would initialize the samples to random values, and then you perform a loop over all these values case, which are the number of Gibbs steps, and then you perform a set of samples many, many times, because you want to find in a way the kind of average probability distribution. And the Gibbs update is then you actually calculating the probability distribution for one of these, given that all the other x's are at the same value as before. This is computationally, normally, if you have a nice analytical expression for the probability distribution, it is normally an easier way computationally. You save cycles, but you repeat this many times to get a best possible representation. Now, when you do this Markov chain Monte Carlo calculations, you often have long correlations times. That means that many of the events may not be stochastically independent of each other. One of the reasons for that is that you're using a pseudo-random number generator, which has correlations built in. So you need often to have a very good random number generator in order to avoid that the random number generators have some correlations in the data. So when you repeat this many, many times, the hope then is that you have a representative set of X's. Then, so that means you're updating the probability of a given X again and again. When you have these X's, then you go back and then you calculate the final gradients. And with the gradients, you update the parameters theta. And then you continue till these parameters theta don't change according to a prefixed quantity which you have set. Now, there are many ways. If you go into the textbook by Goodfellow et al., you will see many ways by which you can perform estimates of the probability distribution. And if some of you have done research on statistical mechanics, you will recognize many of these methods. So one way of doing that is actually a method which was used to sample temperatures, different temperatures, which is called the histogram method. And that means that you calculated a histogram of the distribution of all the variables. And then you use that one to extrapolate to a new, in statistical mechanics, to a new temperature, which was nearby, assuming then that the distribution of variables was more or less the same at a new temperature. And that saved a lot of CPU cycles. That's called the histogram method. And then if you are familiar with the statistical mechanics literature, you will find tons of ways by which people have tried to find quick ways of estimating the probability distribution. So that section 18 or chapter 18 of the textbook contains many of these kind of tricks of the trade. But I think the most important thing for us now is actually to look at the simplicity of the simplest possible implementation. And then you just keep in mind that there are many, many refinements. So I invite you to take a look at that chapter of Goodfellow et al., because that reflects still a lot of the state of the art in the field when it comes to dealing with the probability distributions. So just keep in mind that what we want is a way to evaluate these two quantities. And this is the one which is calculated as an expectation value. So one thing I wanted to, and I'm not going to repeat what we discussed last time about Markov chains. You can just revisit that one if you want to. But I wanted to say a little bit about Gibbs sampling and what it is doing. So there is an excellent set. So this is something which I adapted from a course in Edinburgh. And this shows you how you can understand Gibbs sampling by looking at the conditional probability for a Gaussian. And this is a two-dimensional Gaussian. So a two-dimensional Gaussian means that you have the variable A and the variable B. And that means that your covariance matrix has non-diagonal elements which represent the degree of correlations between variables A and B. And then what you do then is that you sample these two-dimensional Gaussian distribution. You have a mean value for the variable A and a mean variable for variable B. And then you assume that these two A's and B's are correlated. So this is typically the expression which you would have for a normally what you call a multivariate Gaussian distribution. So we've often just seen the standard one-dimensional Gaussian distribution, but in this case, we could have two sets of variables. And what I'm doing now is, and I'm following this example, which I took from these lecture notes, I'm simply setting up this distribution where the mean values are 0 and 0, they have variance of 1, and then I just put in by hand a covariance. So this is just a parameter. I could put it to 0, then there would be no correlations, and then the probability distribution would just be the probability of A multiplied with the probability of B, because there's no covariance. Okay? So what I'm doing here, and this is an example which I borrow from that course, so that simply sets up the covariance, the different variables which I need, And we have used the distribution 0 and 1, and then a covariance, which I put up I'm setting up 1,000 points. And this is what my distribution looks like in 2 dimensions. So these are the points which are now generated by this 2-dimensional Gaussian distribution. And you see that there are degrees of correlations here because I cannot disentangle the 2 variables A and B. Does that sound reasonable? So what I can do then with a Gaussian distribution, I actually have an analytical expression for the conditional probability of A given B or B given A. And then I can do Gibbs sampling for one of these variables. So let's see how we can do that. So this is a kind of test that Gibbs sampling actually gives you back this total probability distribution. So I can then set up my probability, which looks like this. So this is my covariance. This is just a variance. So this would be a more general one. If I have variables A, B, and I can calculate the conditional probability, which has a simple analytical expression. And then I can set it up, the conditional probability, and we can set up the distribution of these, and I can plot it. So this is my Gibbs sampling, where I use the probability, this conditional probability for Gaussians. And when I plot it, I'm now connecting, as you can see here. So Gibbs sampling is that it only updates 1 dimension at a time. As I mentioned, if you go back to this algorithm here, we are just now updating 1 of these variables at a time. All the other ones are kept fixed. So what you see here now is that I'm actually, these functions prior to that one, I'm just updating 1 at a time. And then what I have drawn here is the line connecting sequential samples. So I pick 1 variable, next one, etc. Then the training which I've done can then be compared with the original distribution. So this is my original distribution, and this is a distribution which I get from Gibbs sampling. So you can see here that they look pretty similar. So what I'm doing now is essentially what you see here is an implementation of this algorithm you see here. But instead of calculating the gradients and updating the parameters, I'm simply calculating the probability, because I get new x's. And then every time I do this, it should perfect more and more the probability. And then I do update this one for 1 variable at a time. And when I do that, I actually get something which from here actually looks pretty decent. So it's a way to produce the correct probability distribution, but at a simpler or a lower computational cost. So that's one of the basic ingredients behind the Gibbs sampling. So if I were to use metropolis sampling, I would actually have to calculate the probability distribution of all the variables. And that is much more expensive. So what we are going to do now is actually to look at the explicit equations we get when we are dealing with a binary Boltzmann machine. And then when we are done with that, we are going to point to another way of sampling, which is the Langevin sampling, which is now the kind of sampling which is used in many of these diffusion models and energy-based models. So metropolis sampling and Gibbs samplings are a way to select new events in a Markov chain Monte Carlo machinery. And the Markov chain Monte Carlo machinery is just essential. Without that one, you cannot sample from these complicated probabilities. And this is also the reason why Bayesian statistics has become so widespread, because in the beginning, when Bayesian statistics was introduced, people did not use Markov chain Monte Carlos in order to generate new stochastic events. but they relied much on having analytical expressions, which you then could use to find the posterior probability. But with a Monte Carlo sampling, you can actually use any type of initial probabilities. So anything which you see here is actually a basic element in let's say, Bayesian statistics, yeah?
The Gibbs is sort of similar to stochastic gradient descent. So you have a large sample set and you pick sort of small samples, either in batches or uniquely, and you find your path in your
So what you could say is that it looks very much like stochastic gradient descent, except that stochastic gradient descent doesn't use a Markov chain Monte Carlo. That's a big difference. So that's a very good point. So you will often see in the literature that people say that this is pretty close to what you do with stochastic gradient descent. Any more questions? Good points. So before we move on, I wanted to say a little bit about types of Boltzmann machines. So we've discussed this before with generative models, etc. But let's switch a little bit back to the whiteboard. So if we look at many of these standard Boltzmann machines and the way they were presented, so if you take a look at this function E, which and now I'm skipping the parameters theta, so that's just implicitly there. What we could do, so what we did when we had a binary case, and we had one hidden layer, was simply to assume that we would have a set of biases, which are set to non-zero and a small value, just to get the training going, X plus, and then I had a bias B times H, plus this X of T times the weights times H. So this is a typical binary Boltzmann machine. And that is perhaps one of the more popular ones in the literature. And it's easy to implement. And as you will see just in some few moments, we can calculate analytical expressions for all the probabilities which we need to implement. Now, Boltzmann machines, they could be made more complicated. So you could think of XH, and now you could allow for, let's say, a coupling between the nodes. So you could have couplings in the visible layer. So node X0 couples to X1, and A would then be a matrix with weights. You could do the same here. So that means you could have a H of T times a matrix B instead of a vector, which we have now, and H, and then you would, in addition, have this X of T of W times H. And then you can keep stacking this. So that means you're not limited to one hidden layer. So this is now, if you now stack this, you could now think, if you look at this last model here, suppose we have two hidden layers. So you could have something like this. So this would be the first hidden layer, put a 1 here, an H1. So these are the different nodes here. They can be continuous variables or they can be binaries. Normally in the Boltzmann machines, in order to simplify the training, these nodes are made to be binary nodes, the hidden ones. But you could obviously complicate things. You could give them a continuous description, for instance, by using a Gaussian distribution for these variables. And then we have an H2 of 1, and then an H3 of 1. And here we would have a second hidden layer. So H0 of 2, H1 of 2, and H2 of 2. And then we could have a visible layer. So the number of nodes here is just random. What you could have then, if you look at these different terms, it means that you could have a coupling between these, and that could be given by a parameter A0, A1. And that would be given by parameters in here. So that is possible. And if you look at this expression here, it means that you could have a set of parameters between these ones. So you would have a set of weights, which I'm going to put 1 and then 0, 1, etc. So I'm just putting dots here to indicate that that is a further possibility. I can have the same here. So you can see you can stack hidden layers on top of each other. And then in addition to that, you would have a coupling between these different nodes. And that would be the term which comes from here. And then clearly you could have an additional term. So if we now put a parameter 1 here, we could add a new term here, which has h, and this, and here we would have to put 1. And then we could have the transpose of 1, and we could have a new set of parameters, which then link these guys. So you can make these networks deeper and deeper. So these networks which you see here, this one, has typically been called in the literature for a deep belief network. Because we have couplings, we have intra-layer couplings. If we skip that, then we are back to the standard Boltzmann machines. So the standard restricted Boltzmann machine has only one hidden layer. So what we normally call an RBM. That would then just have H0, H1, H2, and H3. And then we would have X0, X1, and X2 here. And then we have the couplings here. We would have a coupling 0, 0. We would have a coupling 0, 1, and then W0, 2, etc. And then we have the biases in addition. So then we have only one hidden layer. Then it's pretty obvious that you can make a deep Boltzmann machine. So you can stack more layers. So that means that you have more parameters to train. And then you would typically be back to the situation which we had previously with different hidden layers, visible layer. So this would be our X0, X1, X2. And then we would have a coupling here where we have the hidden layer. I'm just writing it, first hidden layer, the second hidden layer, etc., etc. But then the energy function for the last one would simply be a function where we have the biases plus the connections between the different layers. So you have less parameters to train. So in a deep belief network, we would have intra-layer connections as well and interlayer connections. Whereas the standard Boltzmann machine, we only have so-called interlayer connections. So for DBM, then we could have, for this specific case, we could have an energy function, which looks like minus, and then I would have the, I'm just writing this in terms of not putting up all the limits properly. I would have a A, and then I would have a J, and then I would have a BJ for the first layer, and HJ for the first layer. And then I have the connection between the input layer, the visible layer. And then I have the weights for the first layer. And this is multiplied with H of 1. And then I would have the next, the hidden layer, where I have a sum over K. And then I have a C of K of 2 of HJ of 2, plus a final connection between J and K. And then I would have the parameters H, J of 1, and then multiplied with the weights. So here I should have IJ here, of IJ of 2, and then HK of 2. And then you can keep adding. Now the problem is that, and you will see that when you're setting up these probability distributions, is that these quantities become more and more complex. And there is a balance to strike between the computational complexity and the computational expense against the quality of the results which you get. So Boltzmann machines, as I said, they had quite some interest till roughly 2000, 2010, and then the interest has a little bit faded away. And then it woke up again right before COVID with more complex energy type of models, so energy-based models. And then we also had another way to actually perform the sampling. So what I'm going to do now is to abuse a little bit on the slides because there are some mathematical technicalities which show you how you can get the quantities you need to program and how you can get the analytical expressions. So let me switch back to the Jupyter notebook. So the thing which we are going to look at is now a simple binary case. Another case which is used quite often is a so-called Gaussian binary. And this is specifically of interest if you have continuous input variables. So what we are doing now, if you think back to a neural network, in a neural network, you do a forward propagation, and then you back propagate. And every such forward and back propagation, you update the parameters theta by calculating the gradients. Now, what you do here, on the other hand, you give an input x, and then you calculate the derivatives or the functions, but you don't use back propagation. So every time you update the gradient, so there's no back propagation in a Boltzmann machine or in these energy-based models. What you do, you have an input, and then you produce a new input. And then you continue again and again till you found an optimal probability distribution which describes the data. So this is a different philosophy compared with a standard deep neural network, as you have seen before. And I think I put in some of these wordings in the text here. I think I put in some. Yeah, so in energy-based models, you don't use back propagation and automatic differentiation for computing gradients. Instead, you turn actually to Markov chain Monte Carlo methods. That is the big difference. So coming back to the questions about this looks like almost like stochastic gradient descent. So there is a lot of commonality, but the big difference is the usage of Markov chains. So, and a restricted Boltzmann machine has normally just one hidden layer. So you can read through some of that, and but I wanted to give you some of the details. So I'm gonna. This is basically the training which we discussed before. These are the derivatives which we need to set up. I'm not going to go through everything here because I wanted to look at the kind of parameters. You can also add hyperparameters if you want to. But let's now look at the binary Boltzmann machine, because that's the kind of simplest Boltzmann machine which you will encounter essentially in many of the simpler applications. So in this specific case, what you need to calculate is this probability of x and h and theta. And this is simply given, and let me just increase the fonts a little bit. This is now given by this function here, which we also discussed before the break. And this is the partition function. Now, keep in mind now that the x's and the h's, they represent a given configuration. And as we mentioned before the break, just to quickly remind you of that. So let's just go back to the whiteboard. So one of the configurations which we had could be if we have two hidden nodes and two visible nodes. These would be the typical configurations for X, and then you would have a similar configuration for the hidden nodes. They would take the same values if the X and H take binary values 0 and 1. So these are the typical configurations. So when you see this X, And similarly, the H, it actually refers to these possible configurations. So let's just go back to the Jupyter notebook. So this is the definition of the partition function. And then one of the quantities we need to plug in is actually the so-called marginal probability, the probability of X given theta. Because at the end, this is what we want to optimize. This is the quantity we actually want to give somebody who wants to use our model. So at the end, here we can actually perform the calculations. And when you look at this notation here, so let me just increase the fonts a little bit more so that it's more visible. So this strange notation, the asterisk here, let me just quickly say what that means by going back to the Jupyter notebook, now to the whiteboard. So when you look at that specific notation, what I've used as a shorthand here, if we look at this xi multiplied with j multiplied with h, I'm going to rewrite that one in terms of a sum over j, and then I have this x multiplied with w, and then I'm just putting an asterisk here and multiplied with h or j. So this kind of a strange notation here actually takes into account the fact that I've singled out one of the i's. So think of this, because this is actually a vector times a matrix. So what I'm having is a vector x, 0, x1, up to xn minus 1. And this is then multiplied with a matrix with w00, w01, w10, and down here. So it means that when I look at one specific term here, if I take an x of I multiplied, so an x of I would be typically one of these quantities which you have here, multiplied with the pertinent row or column. So this is just more compact notation for the vector matrix multiplication. So let's go back. So what you see now is that I'm singling out the, because I want this specific dependence on the x's. So what I've done here is just to take x times w. So this means that the vector times the pertinent, so this is just a transpose vector times the correct column. And then it has an index j here. Sorry, this is column j, and it multiplies that with the correct row. And then I have an hj here. And then I can rewrite the sum which you have here as a product. You've probably seen this before. And I can now look at the product of all the nodes which I have. And then I'm summing over the specific configurations. And at the end, I can actually rewrite my probability distribution, which I have here, in terms of this expression here. So this is a dependence on x, where I simply have reduced everything here to some simpler functions. I can do the same for the hidden units. So if I do that one, I would perform this exercise. And then when I do the same exercise, instead of having A transpose times X, I have B transpose times H. But now I have the transpose matrix here, because I need to multiply that one with a vector H here. So this is just the same kind of shorthand notation which I'm using. But now I have actually summed away all the x's. So keep in mind that here I've summed away all the h's. So I have an analytical expression. So there is no dependence on the h's here. Okay. And similarly here, there is no longer a dependence on the x's. And then we can calculate the conditional probability, which we need in order to figure out or to perform the Gibbs sampling. So for the Gibbs sampling, we need this quantity here, and the same for the x's. So you can repeat the same exercise because now we have to use Bayes' theorem or Bayes' rule. And then we have the probability divided by the marginal probability. And if we do the same exercise here, we can actually show that this expression here, the marginal probability, is given by this function which you see here. And that is just a probability of the HJs with a given X. And these equations here actually simplify when we are looking at the on-off probabilities. So if you take the on probability, so H is 1. So these are the quantities which make life easier for the explicit Boltzmann machines with a binary-binary coupling. You recognize this as a particular function. If anyone remembers what we call that function? This is sigmoid. So what we would simply do then is just to take these as arguments, and then we have the sigmoid function. And then the case with the Hj equal to 0 is simply 1 minus this function here. And it's pretty easy to, and you see why this model has been so popular, because you have analytical expressions for the probabilities which you need when you're performing the Gibbs sampling. And then you can do exactly the same thing here, the conditional probability. So this is simply 1 minus that probability, and you get simply that expression. And then you would do the same thing with the probabilities for the x's, since this is a binary-binary model. So x times the same values, and you recognize again the sigmoid function, but with a different argument. Then you can make life more complicated, and you will probably hate me if I go through all these details, but I've just added this for the sake of completeness. And then one of the reasons why I also add this is because if you want to make something more complicated, it's not likely that you will get a nice analytical expression for these quantities. But for a binary-binary, Gaussian binary, so the Gaussian binary means that you want the x's to be continuous variables. And then you can again calculate analytical expressions for the marginal probabilities and the conditional probabilities, which are used in Gibbs sampling. And you also need this to actually say what is the probability of x and what is the probability of y with a given value of h. So this is basically the kind of theoretical mathematical machinery which you need in order to set up a Boltzmann machine. So you will find also the marginal probabilities, and then for the probability for the visible units, you would then sum up over all these different quantities. I'm not going to go through these ones, but you can actually set up analytical expressions at the end for it. And it won't be a surprise that for the x's, you end up with a Gaussian distribution. That shouldn't be a surprise. So the comment, the form of these conditional probabilities also explains the name Gaussian and the form of the Gaussian binary energy function. And that's what you see. Then in that specific case, the conditional probability given h is a normal distribution with that specific mean value. So one of the things I was thinking of going, but I see my time is getting close to the end, was more to discuss a simple code where I implement a restricted Boltzmann machine. But I think we can just take that in the beginning of next week, because I also wanted, after that code, I wanted to discuss a little bit more about Langevin sampling. And then the reason why I spent so much time on the Boltzmann machines, even though this is something which is almost seen as outdated now, is that it gives, and I hope you agree with me, a kind of pedagogical input to the more modern energy-based models. And that's going to be also the bridge towards diffusion models for us. So the kind of idea now is to bring up Langevin sampling in the beginning of the next lecture, and then discuss a little bit more in detail the codes. So for the project number 2, if you haven't decided what to do for project number 2, one of the suggestions which you will find is about the usage of these energy-based models on, let's say, data for classifications or other type of problems which you studied in the previous project. If you're not interested in using this, I mean, I hope you still find this useful, because this really brings us in where the future is going. And the future is nowadays, or actually the present, is generative models. That's what everybody talks about. Okay, stop 1 minute before time. That's not possible. Okay, guys. See you next time. Right?